In the previous lecture, we saw that given a locally compact topological space X, which is not compact, there is a host of compact topological space X hat and a continuous map I from X to X hat such that X hat minus I of X is a single point. So let us denote this point by P infinity. And the second condition is I from X to. So the first condition will imply that I of X is an open subset because X hat is host of. And the second condition says that I to I of X is a homeomorphism. So this topological space X hat has the following property. So proposition so let T be a topological space, be a compact topological space. Which contains X as an open subset. So we have a diagram. Sorry, not this. Yeah, so we have a diagram. We have a diagram like this. So there is this map J from X to T, and the image of J is open and open in T and j from x to j of x is a homeomorphism. And similarly, we have this map I from x to x hat. So we have a diagram like this, and then there exists a unique continuous map f from t to x hat such that f compose j is equal to I, and f of t minus j of x is equal to p infinity. So for instance, we can take an example. So suppose x is the open disk in R2, let's say. So then one compactification which contains this is the closed disk, and the one point compactification looks something like this. This is the point at infinity. So in fact, the one point compactification is a sphere, is the sphere, and t minus the image of j. So j is this map, and this is I. So t minus j is this portion in green, and what f does is it collapses this whole collapses to a point, to p infinity. This point is p infinity. So let us prove this proposition. So the map f has been set theoretically defined in the statement of the proposition. So clearly such a map is unique. It's unique. It exists and it is unique. So we only need to show that f is continuous. So note that when we restrict f to j of x, so this is a map from j of x to I of x. This is a homeomorphism. As j and I are homeomorphisms. So we will use this so that V contained in X hat be an open subset. So if P infinity does not belong to V, then it is clear an easy check. that V is contained in I of x and F inverse V is contained in G of x. And this shows that F inverse of V is equal to F restricted to G of x inverse of V, which is open, as F restricted to G of x is a homomorphism. So on the other hand, the second case is P infinity belongs to V. So then x hat minus V is compact and contained in I of x. So once again, so this shows F restricted to J of f x inverse of x hat minus V is compact, because this F inverse is first of all defined, and F restricted to G of x inverse is defined as a map, and it is continuous. So as F restricted to G of x is a homomorphism, so but it is easily checked that F restricted to G of x inverse of x hat minus V is equal to T minus F inverse of V. So this is given to be compact. So as T minus F inverse V is compact, it is closed. This implies that F inverse V is open in T. So this proves F is continuous. So this completes the proof of the proposition. As a corollary, we have the one-point compactification of X is unique. So proof. Suppose we have two such compactifications. Let's say x1 hat and x2 hat. Then, using the above proposition, we have a continuous map f from x1 hat to x2 hat, which is bijective. So since the domain is compact, this implies f is a homomorphism. So let's make a remark that f of p infinity 1 is equal to p infinity 2 by definition, and f is the identity on x. So this proves the uniqueness of the one-point compactification. So, okay. So the above proposition can also be phrased as follows. Follows. The pair x comma the map I from x to x hat is universal. So I haven't explained what universal means among all pairs x comma j from x to t, where j embeds x as an open subset into a compact space x. Compact space T, sorry. So the word universal means that in the collection of all such tuples, x comma j, where j is a map from x to t, which has this property, there is a special one, namely this pair such that all tuples map to this one uniquely. So by a map between tuples, we mean a commutative diagram we will see some more examples of universal elements, but we want to say that, yeah. So before we proceed, let us remark that there is an important class of spaces which are not locally compact. Namely, so these are the infinite dimensional Hilbert spaces. Hilbert spaces or Banach spaces, infinite dimensional Banach spaces. So let's see this. So let x be an infinite dimensional Hilbert space. So if X is locally compact, then there is an R positive such that the, the closure of the ball is compact. So as the map, yeah, we can directly argue with D0R closure. But yeah, so as the map, so X goes to R multiplied with X takes D01 closure to D0R closure homomorphically. This map is a homomorphism on the entire Hilbert space. This implies that D01 bar is compact. But this is not possible as the sequence of orthogonal vectors EI has no convergent subsequence. So recall that we had seen, so recall, so this contradicts the criteria for a metric space to be compact. So now let us get back to our discussion. So we get back to our discussion on universal objects. So let's take another example. So let G be a group and let N be a normal subgroup. So then we have the quotient. Let's call it pi naught from G to G mod n. So we consider the collection of pairs GH phi, where phi from G to H is a group homomorphism such that kernel of phi contains n. So a map between two such pairs is a homomorphism F making the diagram So there's phi 1, there's phi 2, and we need a f which makes this diagram commute. So in this collection, among these objects, so clearly there is a special pair in this collection. Namely, the pair G comma G mod n comma pi naught. Moreover, so this is special in the following sense. Special in the following sense. Given any other pair, G H phi, there is a unique map G G mod n pi naught to G H phi. So this statement that there is such a unique map given any other pair is simply a rephrasing of what we learn in group theory, that is, as kernel of phi contains n, it factors uniquely as unique phi naught. So next, we will see an important example of a universal object in topology. So, but before that, so let X be a set and let tilde be an equivalence relation on X. So let X mod tilde be the set of equivalence classes So then we have the obvious map X to X mod. So this just sends X to its equivalence class. So this map is again universal in the following sense. So suppose f from x to y is a map of sets such that x equivalent to y implies f of x equal to f of y. Or simply stated, f is constant on equivalence classes. So then it factors uniquely as. So far we are only talking about maps of sets. So how is f naught defined? Define f naught as follows. Let alpha in x mod tilde be an equivalence class. So let x in x be any element of this equivalence class. So define f naught of x alpha equal to f of x. So clearly this is well defined. And f naught is uniquely defined. So far in the above discussion, we only had sets. But now we complicate the problem as follows. So suppose X is a topological space and tilde is an equivalence relation on the points of X. So the question we ask is, can we put a topology tau on X mod tilde such that 1. The map pi is continuous and 2 for any continuous map f from x to y, which is constant on equivalence classes, there is a unique f naught. Well, it's just a set theoretic map as of now. Set theoretic map f naught, which makes the diagram commute. So the second condition we need is then f naught should be continuous. So let us make a remark. If we were to only impose condition 1, then the above problem has an easy solution. We just take tau to be the trivial topology on x mod tilde. So the second condition is what complicates matters. And the theorem that we want to prove in this lecture, there is a unique topology tau on x mod tilde which satisfies the above two conditions. So let us prove this. Let us first show that such a tau exists. So let tau be the collection of subsets U contained in x mod tilde such that pi inverse U is open in X. So check that. Tau defines, this is the easy check, a topology on X mod tilde. So obviously the map pi is continuous for the above topology on x mod tilde. So we really need to check the second condition. So let f from x to y be a continuous map which is constant on equivalence classes. So which implies the induced. So this implies we get an induced map So to show f naught is continuous, let W contained in Y be an open subset. So we need to show f naught inverse of W is open in X mod gamma, which is equivalent to showing pi inverse f naught inverse W is open in X. But note that pi inverse f naught inverse W is equal to f inverse W, which is open by the continuity of f. So this implies that f naught is continuous. So next let us show that tau is unique. So suppose there is another topology tau prime on x mod gamma, x mod tilde, which satisfies the above two conditions. So consider this diagram, the following diagram. So we have x, this is a projection map to x mod gamma, x mod tilde. So let this topology be tau prime. So we get an induced set map so that is this dotted arrow, which is obviously the identity. So by property 2, for tau, it follows that the identity map from x mod tilde comma tau to x mod tilde comma tau prime is continuous. So this implies that tau prime is contained in tau. And similarly, we have by property 2 for tau prime, it follows that identity is continuous, which implies tau is contained in tau prime. So this shows that tau is equal to tau prime. So this completes the proof of the theorem. So the space x mod tilde with the above topology or rather the above topology on x mod tilde is called the quotient topology. It's called the quotient topology. So thus the quotient topology has a certain universal property. So we leave it to the reader. We leave it as an exercise to explore this. So we will end the lecture here.